Devin has kindly agreed to present what he is up to. So we'll go through his presentation, and then there's just a couple things to chat about with respect to pull requests, where things are at. And I would also like to give you guys a bit of an update on what we're up to with starting Open Geophysics, which is a GitHub organization for some more general projects that are useful beyond just SimPEG. So pulling out some of the pieces that we can share across different packages like Fatamendo. So we will do that at the end. But I'll let Devin go ahead.
Everyone can hear me okay?
Yeah, you're good.
Yeah, you're good. Okay. Yeah. So I guess thanks for taking the time. I think the way I'm going to do this is maybe just a really brief overview of the background theory, because it's maybe unfamiliar for everybody. And then I was just going to go through the two examples that I made. Kind of shows what the new coding can do. So the core VRM stuff is actually been merged to master. And right now it's just about getting examples and the doc strings, sort of get the supporting documentation so other people can actually use it. But the best way to sort of think about this at first is if you got some kind of inductive time domain survey, you're going to excite the Earth and you're going to get an inductive response, but you're also going to charge the Earth in sort of a magnetic way. So similar or analogous to IP, you get this effect at the late time due to this viscous remnant magnetization. So at the early time, we have the inductive response here.
Are you wanting to show something on your
screen? Yeah.
Are you doing stuff on screen?
I'm going to be doing that basically the whole time. So, yeah. Right. This guy. Yeah, sure. Cool. So, yeah. So everybody sees this?
Yep.
Cool. So, so at the early time, you tend to have this inductive response, and then at the late time, you have the VRM response when you see it. And the theory tells us, and experimentation has told us, that if you were to forward model the inductive response separately, so you could use any of the SIL-mesh codes or analytic solutions, and then you modeled the VRM response independently, which is the problem that I worked on, if you add them together, it very well approximates the response from a conductive and viscous Earth. So this is just an example of decay curves in B and dBdt using the 1D codes. So we can do the full problem in 1D, but we want to move to 3D. So that's a very important point to the theory. So we've already solved this problem. And now with the code that I provided, we're going to be able to solve this guy. So the way I go about doing it is really just the integral equation that we use for mag. You can formulate it using potential fields. And effectively, we just parameterize the off-time magnetization. So that's pretty much the name of the game here. I won't spend too much time talking about mathematical models for this. But the one that seems to do quite well is this log uniform distribution of time relaxation constant. So we've got a mathematical model that describes the magnetic susceptibility. It depends on these three parameters, delta chi, tau1, and tau2. So you would maybe use a Cole model for IP. For this, we tend to use this log uniform decay, or this log uniform distribution. And the reason we do this is because the math is very convenient for us. So just kind of the formulation or how we actually do the forward model is that we can define this model parameter. So if you remember, the susceptibility equation that I had depended on these three parameters. Define a model parameter that's kind of an amalgamation of those. You can parameterize the off-time magnetization in each cell. by basically this time-dependent function, the inducing field in each cell, and this model parameter in each cell. So if I want the magnetization at any time, I can use this, this function here, and this depends on the waveform. So you guys might have some questions about that, and I can talk about it if you're interested, but ultimately, we're able to formulate a problem that is a linear problem. So whether or not I'm interested in predicting B or dB/dt, at a whole bunch of times, I basically take a matrix vector product where A is a really dense matrix and holds all the geometry of the problem. And then T is a sparse, very tall matrix that gives me the response at whatever time I want. So I'm not storing these things explicitly because T is very tall, and then I reproduce scaled A's, and then it becomes prohibitively large to store. So I keep them separate. But effectively, this is the Ford problem. So the first example that I had was that I wanted to Ford model a response from a conductive and magnetically viscous Earth. And so maybe I'll put that to the side and then do this. Yes. Okay. So I decided to make it a model that was just a bunch of 3D Gaussian distributions. I just wanted to make some regions where this viscosity was high and some of the problem or the physical property was small in value. So you can see that on the top line here, sort of a cross section along X, along Y, and then a top view. So there's some regions that we should see the response being pretty large, this VRM, and some places where the response should be smaller. And then I tried to do this as similar as I could to the way that we set up and do the time domain EM problems. So the first thing that you need to do is specify the waveform, because that's going to determine this characteristic decaying behavior. So if it's, say, a step off and you're looking for the B response, it's going to decay as ln t. If it's dB/dt, it'll be 1 over t. And if there's a piecewise linear waveform, you can get the analytic solution for that convolution as well, or a square pulse. So you specifying the waveform, you can even put in your own decay behaviors if you wanted to do something else. So you really do need to specify the waveform. That's the first thing. And then we go through specifying the transmitters and the receivers in the same way. So you make the receiver list and you add that to source lists. In this case, I just did this EM61 survey where I took a dipole source lying about 0.5 meter above the surface of the Earth, and then had a coincident loop source. Let me check that out. I think nobody had questions. So yeah, so then we do the same way. We attach the source list, and then we define the problem. So we put in a mesh. We specify which cells are below the surface. And then the extra thing that we don't have to do, it's a keyword argument, but if the transmitter is really close to the cells, then the primary field is going to be varying a lot within that cell spatially. So there's actually an algorithm to refine the sensitivity so that you're computing the sensitivity of the data with respect to that cell properly, that region. So it doesn't change the size of your model space. It doesn't further discretize. It reevaluates the sensitivity. So that's important. And then just to do the time domain EM response, I just took the analytic solution for a half space, and then I scaled it to add some lateral variability. And sort of this is what we end up getting.
What do you mean like a scale? Like a...
So I just used like a Gaussian distribution again on the surface, kind of a 2D Gaussian distribution. So you can even see the imprint of that in the bottom left corner, just so that you don't have just this homogeneous dB/dt response. Okay. It just seemed like a bit more realistic. I initially modeled it using the SILMesh code, because I wanted to actually add a time domain in the VRM, but it was taking too long, and the transmitter and receiver are so close to the cells that there's sort of an issue of cell size versus how close.
Okay. How big is your a loop here? Where is the source?
The source is every 3 meters, so that there's a coincident loop transmitter receiver every 3 meters within this region.
Oh, so it's like an airborne. So you're not doing a big loop and then.
No, it's it's just like a dipole source, and it's a very small ground-based survey. You just have a coincident loop, so you just. Okay. It's a EM61, right?
Right. Should be fine. The SIL code.
Hope did I accidentally do things?
It looks like you dropped off.
Yeah.
So you just have to reshare.
Reshare. Okay, I'll go into the thing. Find the thing.
Yeah, I'd be curious to see how you set up the SIL code, because I think we should be able to get it to run in a reasonable amount of time.
Right. I think if you're computing the secondary field, I think you need to make sure you compute the secondary field, maybe.
Well, it's time domain.
Oh, okay, it's time domain then. Just I don't think there's a big issue. As long as you go reasonably late time, like not a microsecond. But.
Yeah, this is 10 to the -5.
I think that's fine.
Yeah.
I think there's a way to do it. It was just speed and just sort of trying to get it ready for today.
Yeah, so that's fine.
So anyway, we see the decays from a couple places. One of them is an area over high magnetic viscosity. So we expect this VRM response to be large, and then one where we expect it to be small. So we can see that at early time, both of them exhibit an inductive response. Late times, we see VRM, and that if the VRM response is big, then this sort of crossover happens earlier, and if it's a smaller response, it happens later. And then we just see the decays at, the anomaly at 10 to the -5, 10 to the -4, and 10 to the -3 seconds. So at the early time, we see this VRM, at the inductive. At the late time, we see VRM. And then in this middle plot, we see a combination of the features of both. So this is where this whole thing is going to come in handy, is we want to remove the VRM and get the inductive stuff back. So that's just the forward modeling example. And then the inversion example is basically just a part 2 of this. So the synthetic data are modeled in the same way. We make the exact same predicted data that we did in our forward modeling example. And then we add some noise. And then we take everything after 1 millisecond and we invert it to recover that model parameter that's sort of made up for this problem. And because it's a potential fields problem, we just invert for a surface layer. So the inverse problem is really fast. So this is our true model at the surface, and this is what we get back for an equivalent source layer. And maybe I'll zoom in a little bit. Oh, yeah. Yeah, so if the black line is our observed response, and the blue line is the predicted VRM at all the times from that model we recovered. If we subtract the blue from the black, we get this green line. And as we can see, it lies over top of the true inductive response. So eventually you're going to get a point where the noise is much larger than the signal, but we can see that now we've really isolated that inductive response. And so we could then use all of our time domain EM codes to invert that and get conductive structures. And if we looked at the bottom, we see the total observed response. So there's VRM and EM in it. This is the true inductive response at that time. And then this is what we're able to recover by trying to use this workflow to remove the VRM. So we're able to get rid of, this VRM feature here and stuff up here, but we keep our inductive contribution. So those are the two examples that I have for this. It really just sort of explains why this is useful. So all you have to do is model it separately and just add it to your time domain data if you feel like including it. That's basically it.
What's the equivalent source model? Like that? What do you mean the equivalent source here?
So all I need to do is reproduce the VRM response at all the times and at all the locations. So if you have the mag problem, if I can recover a source that explains the fields that I'm observing, then I can predict the fields anywhere.
Mm-hmm.
I'm doing the same thing here.
So this is just the surface layer.
Yeah.
Right. So you're putting a one layer, and
I'm defining just cells at the surface. So I did my active set is like all of the cells below the surface and above -2 meters or something.
But like for a mag problem, you don't really need that cells, right? Like you're assuming property 0, then you don't really need to put that in, right?
What do you mean?
Oh, like you don't really need to generate the big mesh if you're doing the equivalent source. You just need a one cell up top.
Yeah.
Is that right? Or
I could have made a separate mesh. In this case, I decided to keep the same mesh and then make the active topography cells, just that surface layer.
So you used a mapping.
Yeah.
I see.
So in your inversion, you only invert like a magnetic inverse test media for the top layer. Then only use that part to predict data to do the correction. Is that right?
I think maybe I couldn't hear you very well. It was a little jumbled.
What Dequan said was you're using that just for correction, rather than you're really interested in recovering a model, good model.
Yeah,
You're not interested here. You want to get rid of it to get a better EMC.
Yeah, and for this example, all I'm interested in is removing the signal because it feels like it's the most practical example for people. But you could do a full 3D inversion and you could recover that distribution. And I know I don't want to go into too much detail about it, but that property that I've defined actually is a proxy for how viscous it is, for how mature that soil is. There is actually a correlation between its total susceptibility, like its DC susceptibility, its iron and aluminum content, how mature the bauxite is, and this value. So you could actually use it for this.
But is it geologically makes sense? Is it usually happening on the top layer, like this VRM?
Yeah, because if it's any deeper, the response is so weak compared to the inductive.
No, I'm just let's forget about the response, but the geologically, is that mostly happening in the topsoil, or it could be in a depth?
I think it could be at some depth. I'm not an expert on the genesis of these soils. My understanding is that they're a problem when they're on the surface. So there tends to be, you tend to be able to go into a region and go, oh no, when you do the survey, because you see the red soils and then you know they might be a problem.
Mm-hmm. Like the right side of
yeah, that's exactly it. They're mature laterites.
What makes it tough is you got that data and invert for just EM code, you can fit the data pretty well. And then you're gonna recover a big conductor at that. If I took that data, inverted just using the EM code, I have no idea actually whether I can distinguish that's a VRM or not.
Yeah, so if you had, let's go back to, where is it? This image.
Or can you use a strategy Stogie developed for his thesis, you just use early time to cover something and do subtraction again.
Yeah, this is more like a VRM decoupling. Like if you want to get better EM response, which is opposite way. Process is very similar.
Yeah. So one of the things about the VRM is that it's got this very characteristic decay. So the inductive response, let's say we're looking at dB dt, is it's a half space. It's like t to the -5/2. And for VRM, it's t to the -1. So it's very abrupt, and it maintains that behavior. So if you have enough time channels and your late times aren't super noisy, it's actually quite easy to recognize. But let's say this plot here was cut off at, say,
1
millisecond. Yes, you wouldn't be able to do all this stuff. And then you would think that you have a buried conductor. So it's true. It's important that you have enough late time data to be able to be confident that you can attribute that response to being VRM.
Which is very tough in practice. I think that usually like a warm couple millisecond, even ground like over like a couple milliseconds is hard for like a coil types of, if you're using that squid receiver, you can probably go up to 10 milliseconds or something like that. But but it
really it depends on the relationship between the sensor and like the survey geometry. So in UXO surveys, even if the background resistivity can be quite low. So I used I think it's like 0.1 Siemens per meter. It's a fairly conductive background. So if it's 10 to the -3, you completely obliterate that inductive signal. It would just be all VRM. I mean, we kind of choose the background conductivity in VRM to make a nice, pretty example for you guys. But there is data sets, especially UXO scenarios, where there is no background inductive response. It's just the VRM. You just get that. So it is possible to have those data.
That's great.
But it's true, yeah. Usually it's like 10 to the -4 to 10 to the -2 is sort of where.
Yeah, well, it's a challenging problem, right? It's it's tough, and that's the challenges that we're up against.
Yeah, that is. I think Jim McNay has been working on that a lot too, with trying to decompose it to attribute how much is inductive and how much is VRM.
Thanks, Devin.
Yeah, that's about it. Thanks, guys.
Pretty good, yeah.
Any other questions for Devin, or are you guys good if we?
So there is an example now with the VRM. Is that in the GitHub repository, this example?
On my branch, I've pushed it on my branch, but it's not merged to master.
Okay.
Yeah.
It's coming.
Okay, cool. I'm gonna share my screen. So you guys can see that? Okay. So I just wanted to give, I guess maybe actually let's start with pull requests and just see where things are at, and then we'll jump over to open geophysics. So I know Devin's working on doc strings, so this is in progress, right?
Mm.
This is not ready for review?
No, I'll let you guys know. I just wanted to start it to make sure that things will pass.
Do we have it? Yeah, so this is just in progress, so we'll tag it like that so that we know that it's not ready for review.
Cool.
So I know Sagi's been pushing on the DCIP spectral IP. Is there anything you want to go over with that? Or
no, I think it's passing, but there was one that gravity example is still like in Python 2.7. I'm not sure why it passes for like a PR update and then not for other. Can you go back?
Okay, we can
I think that's just like a timing issue in Travis. That example is like shows a little bit different.
Okay.
For 3.6 and 2.7.
Sure, we can take a look at that.
But other than that, I think, yeah, it's probably like good to be merged. Otherwise, it's going to get bigger and bigger.
Yes.
It's pretty big.
Like that comment, eh? Do we know if he's okay with that?
Have you heard from Craig?
I'll ask Craig. Craig.
Sounds good.
Yeah, because I think that's important. Because if this does change his results, even if it's not changing anything significant, we should get his okay.
Right. Okay.
Cool. Anything else people want to go over with respect to pull requests? No? So on my end, like I'd like to get the DCFP spectral IP in, and then I'll update that for the EM SIL stuff. And then I'd like to try and bring in both the 3D SIL mesh and this pull request. So that'll include the change where the CellGrad stencils are no longer methods, they're properties. So it's just brackets versus not, but that impacts the regularization. So this pull request will take care of that, even though it's EM, it takes care of that as well. And then I've improved some stuff on the fields objects. I think you touched some of that as well, so I'll merge that and probably get you to take a Soggy if you don't mind.
Okay.
So I'll make some comments and sort of do a first pass on this before sending it to you guys.
Yeah, we have some example of 3D SIL code, right?
I don't. No, I haven't actually put one in here. I'll add an example.
Yeah, it'll be good to have that one to review.
Yeah, for sure. I will add an example. So, Dom and Deequan, was there anything on your end that you wanted to talk about here?
Not here.
Okay.
Well, I know, like I've been very bad at pushing those PRs, but it will come at some point.
No worries. Yeah, just like when there's updates, we'll go through them. But if not, no problem. Okay, so the other thing that I wanted to talk to you guys about and get people to jump in where they're interested is open geophysics. So this is a GitHub organization that we've started to start collaborating with other projects more so. So we've been in close contact with Leo as well as with Dieter on how do we combine efforts on some of these things, as well as how do we start writing a high-level API for inversions? So, because right now, to hand somebody SimPEG, like you need a driver, you need some serious examples to get somebody up and running, and yeah, it's a high bar of entry at this point.
It's still fun though.
It is, yeah. Well, but you know how to poke around with code. So a lot of the target users definitely don't. Or like they're comfortable working with something like scikit-learn, where I format my inputs correctly and then it does stuff under the hood. Same tuning parameters and stuff were chosen for me, and then I can go play with that. So some of that conversation is happening in this Deep Look repository right now, which may or may not get renamed just to inversion. We're thinking about that. So that's what that is. Matrix utils is we're pulling out some of the utilities like mesh tensor, those kinds of things, makevec and dgrid to this repo because we use them everywhere, and like you don't necessarily the import structure right now is weird, but they're useful beyond just discretizing SimPEG. So those will go there. Test IPython B. This is something I'm kind of excited about because I pulled out all of the code that actually sort of abstracted what we were doing for like the EM examples and the EM apps for all of those tests, and I've actually pulled it into a standalone repository so that if you have a repo of notebooks that you want to unit test, you can do that, and it'll do all of the proper, like when you look at it on Travis, it'll catch like the error that would have been displayed in Jupyter, and then it actually prints it and with all the syntax highlighting and everything that they would use. So it's pretty easy to tell, like if I've set up and I'm distributing a collection of notebooks and I want to make sure that my requirements file is full. So in this case, I have forgotten to include PyMat solver in my requirements file. And so that's like very easy to catch. And so there's one example that you guys can check out. So there's a little bit of usage there, and then I'm using it for the Airborne EM notebooks that we've distributed. So if you want to like have a look and just see, one use case of it, you can see how I set up the Travis file and my tests and all of that. And so like I would love feedback on this. This was really a very first pass. And so if you try it out and find something funky or find something that you like want it to do that it doesn't currently do, feedback would be welcome.
That's great.
Yeah, so that's kind of exciting. And some of the Jupyter folks are excited about it, so that's cool. So I'll chat with them about that when I'm down there at the end of the month. And then the last one right now is the objective function side of things. And so this, we're going to try and pull out some of that core work that we've done on the objective functions. Because that is potentially quite useful for other inversion packages. So, if we write, like if Dom's written the sparse norm stuff, it would be really cool if Leo could use that with Fadiendo. And so that is the conversation that's going on here. Yeah, so there's a few issues and things like that are being posted. So if you guys are interested in helping define what this restructuring looks like and where things live, just jump in on these issues and make some comments. So right now we're not necessarily committing much code. It's very much conversational and like figuring out where things should live. So if that's something you're interested in getting involved in,
That's great.
Lindsay, can I say something?
yeah, for sure.
The timing is kind of amazing because we're talking to MDRU. Diane Mitchelton's gonna most likely come back to UBC to do, well, we have to finalize it, I guess, with Doug, need to approve, but she would be kind of like creating a layer between us and the MDRU.
Yeah.
I was thinking like she could publish a lot of like learning material through notebooks.
Yep.
And it looks like your test at IPython repository would be perfect for that because we'll need to test everything that she's going to be writing.
Yeah. I was talking a bit with Craig yesterday too. He's stoked about getting involved with SimPEG, and I think Diane would be like the perfect person potentially. I don't know her, but it sounds like she'd be a great person to really seriously connect these two groups.
I think she'll have a little bit of a programming curve, but at the beginning, but she's definitely knowledgeable about everything that is geoscience.
Yeah.
So yeah, I think that the timing is perfect. What came out with your conversation with Craig?
It was a brief conversation. It was mostly just enthusiasm.
That's important.
Which is good. But I did tell him we were looking at, developing this higher level API, and I think that's a really good thing as well. Do you know when she was potentially coming? If that's in the next few months?
I think it's pretty soon. Sorry, so you're saying?
No. Go ahead.
Yeah, I think it's going to be pretty quick. I had also like about Fatiando. So I started looking into the filters that he wrote in his library.
Yep.
Maybe some of it would need a little bit of work. Is this Open Geophysics the best place to do this, or we should talk directly on his repo, or what do you think?
Oh, for filters?
Yeah. Like because you're gonna have a lot of like data processing to be done, right?
Yeah. Let's start that in Open Geophysics.
Okay, that sounds good.
Yeah. So maybe, and you know what? You could even create an issue in both places and link them. Like I think that's also totally appropriate. Okay. Yeah. Because we don't actually have processing here yet, but that's a piece that we could pull over once it's scoped. Yeah, so maybe Dom starting an issue like on deep look and then as well potentially linking that to an issue in Fadiendo.
Okay, yeah, sounds good. I'll ping him on the issues, and then we can start talking there.
Okay, that sounds good.
Perfect.
Cool. Any questions about this? Initial thoughts or?
What's actually it testing? Like what does it do? Is it just run
test IPyMD?
Yeah.
It tests that it runs. So that's it. Yeah, I mean, what you can do, and this I might try and do for publications, is include some assert statements. So like assert that, whatever I just ran equals some downloaded stored results. So you can do some things like that that actually sort of turn it into a test. Right. But right now, all it does is make sure it gets from A to Z.
Right.
So, which is still useful.
That's important.
Yeah. Well, especially, because and I'm guilty of this when I'm working in my research notebooks is, you execute cells 1 to 10, then you execute 15, 10 again. And so if you actually hand it to somebody and say, run this in order, it doesn't work. So those kinds of things get common.
And then would it run again the tests when the libraries are updated, or do you have to do it manually?
You'd have to do it manually, but one thing that can help with that is if you turn on Travis cron jobs. So if you go to Travis, and we can look at the SimPEG settings, for example. We run a test every month on master, irrespective of if it's changed. So if we look here at more options, settings. So here, cron jobs. So on master, it runs every month. And it's, you can configure the settings. So in this case, we don't run it if there was a test within a couple of days. But on things like research repositories, it's nice because you can just have your notebooks that are associated with your publication and then just turn on the cron job. And basically, you'll get an email if in 3 months NumPy updates something that you need to fix. So.
Yeah, that's perfect. Good job.
Well, it was definitely all part of the GeoSci stuff, but then it was nice to actually take a moment to clean it up.
So, can I keep talking about this?
Mm-hmm.
Where do you think we should? I was thinking GeoSci.xyz could be a place to start putting stuff for Diane. You think it's a good place, or?
Putting notebooks?
Yeah, like training material, or not entirely sure how it's going to look, but we need somewhere that we can store and deploy or show those notebooks.
And these would be more so on, it's more general than SimPEG, hey? It would be basically on integrating geophysics and geology.
Correct.
Yeah, I think that GeoSci is probably a good place for that.
Sounds good.
Yeah, we can start a repo and even just start sketching issues and scope and things like that.
Yeah, I think that will be super useful for her if we can just set up the infrastructure and then give her a space where she can lay out all the things that she wants to do.
Yeah.
So we don't need to deal with Word documents and all that stuff. We can take her right away to the 21st century.
That sounds like a very good idea. Sure, we can brainstorm after maybe offline and just come up with an appropriate repo name and what should be in there to start with.
Yeah, perfect. Yeah, I'll come in tomorrow. So.
Okay, that sounds good.
We should talk. Yeah.
And do you know Diane personally?
Yeah, I was working with her at Mira.
Okay, cool.
Yeah.
Nice. Well, that's exciting. Any other things? I think so. Yeah, I think that's basically it for now. Cool. Deequan, Dom, anything else you guys wanted to chat about today?
No, not for now. Yeah, mostly working on some theoretical stuff. Haven't been programming for a while.
Yeah, nothing on my end either. Just doing other stuff.
Okay. Anything else from you guys?
Like, I'm not going to talk today, but I'm working on the time domain code for like a 1D time domain code.
Oh yeah.
So so Dom and I worked on that laterally constrained version.
Yeah.
So actually that part is done.
Nice.
So time domain is done.
Yeah.
Like, so I was working hard on that. Yeah, so, like, I was interested more like practical issues, like all the system, like how to model the system parameters and stuff, like repetitive waveforms and low-pass filters and that types of stuff. So I'm getting pretty close.
Nice.
So actually, I got most of things working, and I'm going to talk about it at one point, probably next week or something.
Yeah, if you want to talk about it next week, that'd be awesome. Where does all that live right now? Is it on the SimPEG organization?
No, it's in the SimPEG under SimPEG EM1D.
Okay, cool.
So anyone wants to check.
Have you guys heard back from Jared?
Nothing more yet. I think he is in the field this week. I know that he was leaving like Friday afternoon or over the weekend. So we may not hear anything for a little while.
Yeah, that makes sense.
Okay. Cool. Well, thanks for your time, everyone. We will see you next week.
Wow, 54 minutes.
Okay, thank you guys.
Short meeting.
Yeah. My time.
Yeah. Have a good day.
Bye guys.
Okay, see ya.
Guys.